Welcome back to The Deep Dive, where we take the most complex, boundary-pushing ideas in science and philosophy, extract the core nuggets of insight, and package them up just for you.
And today, wow, we're not just exploring the cosmos.
No, we're questioning the very fabric of existence itself. We are taking a pretty big jump off the cosmological deep end.
That's a good way to put it. We're moving far beyond the, observable puzzles of black holes and dark matter.
Right.
We're diving straight into the ultimate ontological question. What is reality fundamentally made of? Is it particles? Is it quantum foam? Is it strings vibrating in 11 dimensions?
Or is the universe, at its deepest, most fundamental level, just math?
That's the question.
And that's the hook that gets us all right. What if the profound laws of physics aren't simply described by mathematics?
Which is how we usually think of it.
Exactly. But what if the physical reality is the mathematics itself? Today we're tackling the radical, unified claim made by MIT cosmologist Max Tegmark.
It's known as the mathematical universe hypothesis, or the MUH for short.
And it is Platonism taken to its absolute logical extreme.
It really is. So our mission for this deep dive is to unpack the rigorous two-step logical progression Tegmark uses to argue for this identity claim: physics equals mathematics.
And then we have to place it. We have to situate this whole thesis within the current, very strange landscape of modern cosmology. I'm talking about the hierarchy of multiverse theories.
And finally, we'll spend a good amount of time exploring why this theory, which Tegmark claims is the only baggage-free explanation left, has caused such intense polarization.
And some really rigorous technical challenges in the scientific community.
Yeah, it is not without its critics.
Not at all. And the initial intrigue here is just so beautiful because it attacks a problem that has puzzled scientists and philosophers for centuries.
The big one.
Why does math work so perfectly to describe reality? Why is it so, as the physicist Eugene Wigner put it, unreasonably effective?
And the MUH provides this startling, almost tautological answer that just dissolves the mystery altogether. So let's get into the genesis of this problem.
To really understand the, I guess, philosophical and scientific desperation that would compel someone like Max Tegmark to propose such a radical idea, you have to realize this tension is ancient.
Oh, absolutely. The tension between abstract math and, tangible physics.
We're talking about 2 millennia of philosophical wrestling.
It truly is. At the very heart of natural philosophy, going all the way back to the ancient Greeks, was this central question. What is the relationship between the realm of perfect eternal abstraction and the messy, changing, tangible physical world we see around us?
And the earliest and maybe the most radical answer came from the Pythagorean school.
Exactly. The Pythagoreans asserted quite boldly that all is number.
Which is a huge claim. They weren't just saying that numbers help us understand the world.
No, not at all. They believed mathematics was the fundamental architecture, the actual substance of reality. They found this divine harmony in musical ratios, in the geometry of shapes, and especially in the predictable perfect orbits of the celestial bodies.
For them, math was the hidden, eternal scaffolding of everything. But then, over time, that idea, that mathematical monism, it got kind of superseded.
By the rise of Aristotelian empiricism, Aristotle basically shifted the whole focus.
He did. Aristotle argued that math is merely a descriptive tool. It's a language we invent and refine to categorize, measure, and understand the sensory data we collect about the physical world.
So for Aristotle, math is the map, a highly effective one, but it is not the territory.
And that dualism, math as map, physics as territory, that really persisted. It went all the way through the Enlightenment and the foundations of classical physics with Newton.
Right. The laws of motion, gravity, they were all written in mathematical language, but the assumption was always that gravity itself was a physical force operating on physical masses.
And the equations just helped us track the process.
But then modern physics arrived, and that assumption started to feel, well, pretty inadequate.
It did, because the math became indispensable in ways that went way beyond mere description. The modern statement of this profound unease, comes from the Nobel laureate Eugene Wigner.
In 1960, right?
Yes, in 1960, he wrote the seminal paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, which you could argue is the spiritual starting point for the MUH.
I love that title because it just captures the astonishment perfectly. Why did Wigner call it unreasonable? What was so unreasonable about it?
It was the miracle, the sheer coincidence he found so disturbing.
Mm-hmm.
He observed the fact that mathematicians would often develop these incredibly complex, esoteric concepts purely out of intellectual curiosity.
With absolutely zero physical application in mind.
None whatsoever. Things like group theory, or non-Euclidean geometry, or even matrix algebra, decades before quantum mechanics was a thing. And then, decades or even centuries later, those exact concepts become absolutely essential for describing fundamental physical phenomena.
It's like discovering the keys to the cosmos were just sitting in a dusty drawer in a university library, invented by someone who had no idea what they would eventually unlock.
Precisely. Wigner called this the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve.
Wow.
It felt like a coincidence of such staggering, miraculous magnitude that it defied any conventional, non-mystical explanation.
And Tegmark looks at that quote, at that sense of awe and confusion, and says, if it's unreasonable, let's find the only ontological explanation that makes it reasonable.
That's the core motivation. The MUH is a direct and forceful answer to Wigner's puzzle. If we stick with the conventional idea that math is a human invention applied to a non-mathematical reality, its effectiveness is a profound mystery, a lucky break.
But if you accept that the universe is a mathematical structure,
then its effectiveness is tautological.
right?
It works because the map and the territory are the same substance. The dualism just vanishes.
Okay, but before Tegmark's radical leap, other thinkers tried to offer more conventional, less out-there explanations for why math works so well.
Yes, people like Richard Hamming. It's worth going through them because they represent the standard skeptical view.
What were some of his ideas?
Well, Hamming suggested a few things designed to reduce Wigner's miracle to, mere human psychology or selection. The first was selection bias.
Meaning we only look for mathematical patterns, so of course we find them.
Right. If we tried to describe physics using poetry, we would find patterns in poetry.
Which sounds plausible at first, but then you realize the math often requires this immense technical difficulty, far beyond simple pattern recognition, to even discover in the first place.
The second was tool selection. The idea that we invent math only when physics demands it. So Newton invented calculus because he needed to describe instantaneous change.
But that fails what you might call the prophecy test. Newton didn't invent tensor calculus, but that was absolutely required for general relativity centuries later.
Correct. The third was limited scope. Math only describes the parts of reality that are, susceptible to quantification, and it ignores things like ethics or meaning or subjective experience.
And the last one.
Evolutionary priming. That our brains are basically just pattern recognition systems honed by evolution for survival, and math is just the formalization of that biologically useful skill.
While all of these offer a degree of comfort, they all seem to fail the ultimate test, which is deep predictive power, especially when you look at the history of physics in the 20th and 21st centuries.
Absolutely. The greatest weakness of all these conventional explanations is their failure to account for math's ability to predict phenomena completely alien to human sensory or evolutionary experience.
I mean, if math were simply a formalized system for counting and survival, how could it possibly lead to the prediction of things that exist so far outside the human scale?
Give us a powerful example of that alien experience.
General relativity is the supreme example. When Einstein was developing his field equations, he was working purely from abstract mathematical principles. Things like consistency, symmetry, and the realization that space-time must be dynamic.
He wasn't working from some new experimental data.
No, it was pure thought. And his equations, derived purely from that mathematical consistency, predicted the existence of gravitational waves and black holes.
Phenomena that were purely theoretical mathematical derivations for decades before our technology could actually observe them.
Right. Black holes are a long way from the survival mechanisms needed by early humans on the savannah. Gravitational waves are these incredibly subtle ripples in space-time.
Exactly. So if math were merely an adaptive human tool, how could it unveil the cosmos structure across these immense and unobservable scales? From the tiny 10 to the minus 35 meters of the Planck length.
All the way up to the 10 to the 26 meters of the Hubble scale.
This ability to unveil the hidden structure, using concepts that were entirely abstract when they were formulated, it demands a much stronger ontological explanation than just lucky coincidence.
And the MUH provides that stronger explanation. It asserts the ultimate identity. Physics is mathematics.
So, okay, let's trace Tegmark's rigorous logical path. If the MUH is the solution to Wigner's puzzle, how does he get from the standard assumptions of science to this radical conclusion?
That physical reality is a mathematical structure, not just described by one.
He builds his whole argument on two foundational pillars.
Okay, I'm ready for the pillars. Let's lay them out. And I think we need to give enough rhetorical weight to the profound implications of each step.
This is a big deal.
It is. Pillar 1 is the external reality hypothesis, or ERH. This is the starting assumption, and it's absolutely essential.
What's the definition?
There exists an external physical reality completely independent of us humans.
Which is the bedrock of scientific realism, right? I mean, if we reject this, science as we know it becomes impossible because we can't trust our observations or the stability of natural law.
We'd be trapped in solipsism or some kind of radical constructivism where reality is just what we make it.
So Tegmark insists we take the consequence of this independence seriously, really seriously. If reality is truly external, if it would be the exact same structure, even if humans had never evolved, then the ultimate description of that reality must be free of everything subjective.
It must be free of what he calls human baggage.
Yes. And that sets the stage for Pillar 2, the purification of description. This is where the identity claim really hinges. We have to explore this human baggage in detail.
Let's do it. What does he mean by that?
Well, think about our current physical theories. We use this sort of hybrid, messy language. We have the beautiful mathematical structure of the Standard Model, written in Lagrangians and symmetry groups.
The pure math part.
Right. But then to talk about it, we attach all these sensory-rooted metaphors to the abstract entities. We talk about a quark's flavor or its color charge or an electron's spin.
And these terms are great for intuition, but they're subjective metaphors. The color charge of a quark doesn't look like the color red.
Of course not. It's just a mathematical property defined by the SU3 symmetry group. An electron spin doesn't mean it's physically rotating like a little ball.
Right, it's a quantum property. Or take the concept of force. We use language like the Earth pulls on the moon. That implies a physical tug.
But in general relativity, that force is completely replaced by a purely mathematical concept. Space-time curvature. The force vanishes. The mathematical relation is all that remains.
So the thought experiment here is profound. We have to systematically strip away all of that language. We remove all metaphors, all sensory inputs, all cultural history, all human intuition. We purify the description.
And what is the absolute bare residue that must remain if reality is truly external and independent of us?
What's left?
What remains is purely a set of abstract entities and the relations between them. The entities might just be placeholders, locations in a manifold, vector components in a field. And the relations are the rules that define how those placeholders connect. Addition, differentiation, successor functions, topological proximity.
This residue is what physics must be, independent of us.
And the key conceptual jump, the punchline, is that baggage-free description, a collection of abstract entities defined solely by the relations between them, is literally the textbook definition of a mathematical structure.
There it is.
It is. Tegmark argues that if the only coherent, independent description of reality is a mathematical structure, then reality is that structure. This is the identity relation. Physics equals mathematics.
He proposes that reality is isomorphic to a specific mathematical structure.
Let's spend a moment on isomorphism, because that word is the cornerstone of his entire argument. It's a lot more than just similarity, right?
Much, much stronger. Isomorphism means there is a perfect one-to-one correspondence between two structures that preserves all of their relations.
So if the universe, let's call it A, is isomorphic to a mathematical structure, B, then every element, every property, and every rule governing A is mirrored perfectly in B and vice versa.
They are structurally identical.
Which means we aren't just saying math is a fantastic model, we're saying the mathematical structure is the thing being modeled. And this radically alters the universe's ontology. The stuff is gone.
The stuff is gone. So the universe's fundamental nature is not some primordial non-mathematical substance. It's not a hidden physical layer, not energy, not even a hidden layer of strings.
The mathematical relations are the substance.
Okay, let's use the electron example to make this really concrete for you listening. How does the electron function under the MUH?
Well, we traditionally think of an electron as a tiny ball that has properties attached to it. Mass, charge, spin.
Stuff with properties.
In the MUH, that conceptual baggage is stripped away. The electron is not a ball. It is purely a mathematical object, a set of relational properties defined entirely by its quantum numbers and asymmetry properties within the structure's defining group, which is SU2 times U1.
So its mass isn't something added to it. Its mass is its mathematical relation to the Higgs field. Its charge is its relation to the electromagnetic field.
Exactly. If you remove the mathematical relations, the electron simply ceases to exist. Its existence is its mathematical definition and its relational properties within the overall structure.
The universe is therefore a Platonic realm made real, where the abstract forms of mathematics are the literal components of reality.
That's a profound derivation of identity. Now, we have to place this idea within the context of modern physics because Tegmark frames the MUH as the final, necessary step in a hierarchy of multiverse theories.
Right, levels 1, 2, and 3 are increasingly accepted by mainstream cosmology. The MUH, level 4, is presented as the necessary apex.
That progression is key. We start with level 1, which is almost non-controversial, and then we climb this ladder of conceptual complexity. And level 4 is situated to answer the ultimate question that the other three cannot.
Which is?
Why these specific mathematical equations?
Let's start with level 1, the regions beyond our horizon. This is based entirely on conservative assumptions about standard cosmology.
Level I simply assumes that space is either infinite or, just sufficiently much larger than our observable Hubble volume. It also assumes that matter is distributed roughly uniformly on the largest scales.
The ergodic assumption.
Yes. And if space is infinite and the possibilities for arranging matter and energy within a finite volume, say a sphere the size of our visible universe, are finite,
then the arrangement must repeat.
It's a certainty, just based on probability and combinatorics. Due to quantum uncertainty, there is a staggeringly large but ultimately finite number of ways to arrange the particles within a Hubble volume.
Something like 10 to the power of 10 to the power of 122 states.
An insane number, but finite. In an infinite space, those patterns must repeat infinitely often.
So somewhere out there, approximately 10 to the 29 meters away, sits a cosmic region where the particles have arranged themselves identically.
Which means a duplicate of Earth and a duplicate of you down to the precise state of your brain matter must exist.
That's a stunning implication. But what's crucial to understand here is that level I parallel universes are just distant regions of our space.
Right. They are governed by the exact same fundamental laws and physical constants we observe right here. They only differ in their initial conditions and the arbitrary arrangement of matter.
That scale is so immense, it's almost an abstract concept, but scientifically, it's a straightforward probability argument. Now, level 2 is where the real diversity in the multiverse comes in.
Level 2 involves bubbles of eternal inflation. This relies on the theory of chaotic eternal inflation, which is a widely considered extension of inflationary cosmology.
How does that work?
The idea is that the high-energy false vacuum state is perpetually expanding, and occasionally it decays locally into stable, true vacuum bubbles. Our universe is one such bubble.
And why does this mechanism create universes with different physical rules?
Because when that transition occurs, when the high-energy field relaxes into the low-energy state, it's like a phase transition. The process of symmetry breaking can happen differently in each resulting bubble.
And this variation means the effective laws of physics can change.
Yes, we're talking about core properties. The number of spatial dimensions, the fundamental strength of gravity, or even the precise value of the electron's mass.
So the cosmological constants that make our universe habitable, like the electron mass or the strength of the strong nuclear force, are often seen as these arbitrary parameters.
And level 2 provides a very compelling solution for this arbitrariness. It's known as the anthropic principle.
Fine-tuning problem. If gravity were just slightly stronger, or the Higgs field slightly different, stars and stable atoms couldn't form, and life would be impossible.
The level 2 multiverse says we simply exist in one of the bio-friendly bubbles because, by definition, we can't observe or exist in the others. The whole ensemble of level 2 universes explains the apparent fine-tuning by turning constants into variables.
Okay, that brings us to level 3, the quantum many-worlds interpretation.
Or MWI. Level 3 is based on the MWI, which was proposed by Hugh Everett back in the 1950s. It argues that the quantum wave function never collapses. Instead, every time a quantum event has multiple possible outcomes, say a particle being spin up or spin down, the universe doesn't choose one, it splits.
And all possible outcomes are physically realized in different non-interacting branches in a shared Hilbert space.
This creates an unimaginable number of parallel universes branching out constantly, including a universe where you decided to skip this deep dive today.
A terrible universe.
A terrible universe. But here's where Tegmark makes a critical observation that sets up the need for level 4. He argues that level 3 adds nothing qualitatively near to the total collection of possibilities that are already present in level 1.
How can that be? Level 3 seems so much more prolific.
Well, Tegmark argues that the universes generated by level 3, the splitting branches, are simply realizing the same set of initial conditions and physical laws inherent in level 1. Their location is just different.
Okay, explain that difference.
Level I universes are far away in physical space. Level 3 universes are merely non-interacting branches in an abstract mathematical space, Hilbert space. His famous summary is, the only difference between level I and level 3 is where your doppelgangers reside.
But both levels are governed by the same overarching fundamental math.
Exactly. So no matter how many parallel universes levels 1, 2, or 3 generate, they all rely on the same fixed set of core fundamental equations, the master theory of everything that governs them all.
And that leads to the ultimate question that necessitates the radical leap to level 4.
Why that specific set of equations? Why the laws we observe, rather than some other mathematically consistent set?
Why complex numbers and not quaternions? Why 11 dimensions in string theory and not 12? Any choice of a fundamental theory of everything seems ultimately arbitrary. It's the final free parameter.
And to eliminate this last vestige of arbitrariness, this last free parameter, the conclusion must be
that all mathematical structures that are internally self-consistent exist physically.
that is the ultimate ensemble, the level 5 multiverse, and it is the mathematical universe hypothesis.
So this elevates the MUH from a theory about our universe to a theory about all possible universes. Our universe is just one specific, recognizable mathematical structure within an infinite set of possible structures defined by all possible self-consistent axioms.
And if a structure is complex enough to contain observers, or what he calls self-aware substructures, then it is experienced as real. The MUH solves the puzzle of arbitrariness by asserting that there is no singular theory of everything.
Only the ensemble of everything.
Okay, this is the hurdle for most people trying to grasp the MUH. It's a big one.
I can see why. If reality is truly a cold, abstract, static mathematical structure, why do we, the inhabitants, experience things like flow and change and emotion and the piercing feeling of now?
It doesn't feel like we're living inside an equation.
Not at all. And that profound disconnect between the objective structure and our subjective experience requires a critical distinction.
And Tegmark addresses this. He uses the vivid analogy of the bird's eye view versus the frog's eye view. This distinction is absolutely essential to connect the abstract mathematics to the messy reality we all perceive.
Let's start with the bird. That is the perspective of the mathematical structure itself, the
Right.
objective reality.
The bird's eye view is the timeless, complete perspective. It's the view from nowhere. From this vantage point, the mathematical structure is static and eternally complete. It does not evolve or change or move.
And time is not a flow.
No, it's simply a coordinate, like the spatial dimensions X, Y, and Z. All events, the earliest moments of the Big Bang, the moment you were listening to this, the final heat death of the universe, they all exist simultaneously within a fixed four-dimensional block universe manifold.
So from the bird's perspective, the future is already determined and exists just like the past already exists. It's simply a different point on the time coordinate. There's no element of change or creation.
Absolutely. The structure exists eternally in the Platonic sense. It is necessary. Furthermore, the bird's view often perceives a high degree of mathematical symmetry. For instance, the universe's global wave function might be a perfectly symmetrical and static, pristine mathematical object.
But the moment we move into the frog's perspective, the world fundamentally changes. We see flow and asymmetry and change.
That's the frog's eye view. We are the self-aware substructures, the SAS embedded within the math. And the frog's experience is fundamentally about information processing.
Because the SAS are complex brain patterns processes information sequentially along that time coordinate axis, we are tricked into perceiving a flow of time. We experience duration and causality.
I think the analogy of the movie reel or the DVD is critical here to really grasp why the flow is an illusion of processing.
It's a perfect analogy. Imagine a massive hard drive containing a movie that runs for 14 billion years. That hard drive is a static object. That's the bird's view. All the information, all the frames exist simultaneously.
But when you, the observer, the SAS, run the data through a processor, you experience the sequential movement, the plot, and the flow from beginning to end.
The perception of flow is an artifact of the sequential processing mechanism, not a fundamental property of the hard drive itself.
So our consciousness, that feeling of now, of temporal immediacy, is simply the location of our information processing pattern as it travels along the coordinate of time.
Yes, that feeling of immediacy, of existence in the present moment, is what it feels like to be a complex information pattern inside the math.
And furthermore, the frog's view is what perceives a single, classical reality. This is thanks to quantum decoherence.
So while the bird sees the beautiful superposition of all possible states,
The SAS, by virtue of interacting with its environment, perceives only one specific classical branch. The frog sees broken symmetry, which masks the perfect mathematical symmetry of the bird's total structure.
this really deepens the philosophical question of subjectivity, or qualia, the private internal feelings like the subjective experience of pain or the taste of chocolate or the sensation of the color red. Are these two just mathematical patterns?
According to the MUH, yes. Qualia, emotions, consciousness itself, they are valid internal perceptions, but they are not fundamental ontological ingredients of the universe. They are high-level artifacts of the complex recursive data processing performed by the SAS.
So the fire of existence, that intense qualitative feeling of being alive, is simply the user interface.
Exactly. It's the subjective user interface generated by the mathematical pattern of our brain structure processing data.
Yeah.
They are structurally defined. If two SAS structures are mathematically isomorphic, meaning they have the exact same functional relationships and information flow, they would necessarily experience the exact same qualia.
Regardless of what they are made of.
Yes. And this leads directly into the AI connection we'll discuss later. Consciousness is substrate independent because it's a pattern, not a substance.
As profound and unifying as the MUH is philosophically, its journey into the scientific mainstream meets some severe technical friction.
Right, when it's confronted with the powerful constraints of mathematical logic. Tegmark isn't just making a philosophical statement, he's making a claim about the set of all existing realities, and that set has to obey certain logical laws.
So let's start with the biggest logical bomb that can be dropped on any formal system: Gödel's incompleteness theorems. How do physicists argue that the MUH is incompatible with Gödel's results?
Physicists like Pete Hutt and Mark Alford argue that if the universe is a mathematical system, and it is a system complex enough to contain elementary arithmetic, which it clearly is, otherwise we couldn't count, then Gödel's theorem must apply to it.
Can you just remind everyone of the core dilemma that Gödel proved back in the 1930s?
Gödel proved that any formal system powerful enough to contain arithmetic must suffer from one of two fates. It is either inconsistent, meaning it contains contradictions where you can prove both A and not A.
Or it's incomplete.
Right, meaning it contains true statements that are fundamentally unprovable within that system.
And neither of those sounds like a very stable foundation for reality. If the universe is the mathematical structure, then reality must be fundamentally contradictory or fundamentally unknowable.
That's the severity of the challenge. Does physics contain undecided propositions? Could there be a physical process that, even with perfect knowledge of the initial conditions, leads to an outcome that is neither mathematically provable nor refutable?
That would violate the determinism and completeness we typically assume for a fundamental theory of everything.
It would. So how does Tegmark attempt to save the MUH from being infected by this Gödelian virus?
What's the fix?
He proposes a critical modification, retreating slightly from the most maximalist claim. He restricts the ultimate ensemble to only those structures that are computable.
And this restriction forms the computable universe hypothesis, or CUH.
That seems like a necessary restriction, but we need to define computable clearly in this context.
Okay, what does it mean?
A mathematical structure is defined as computable if all its relationships, its states, its transitions, its rules, can be computed by a theoretical machine, specifically a Turing machine, in a finite amount of time.
So if a structure is computable, it avoids the paradoxes of undecidability and inconsistency that arise in infinitely complex or self-referential mathematical systems.
Exactly. It suggests our universe is fundamentally discrete or digital at the Planck scale.
But this restriction immediately draws the most powerful critique against the CUH. By restricting existence to only the computable subset of mathematics, hasn't Tegmark reintroduced the exact problem the MUH was designed to solve? Arbitrariness.
Absolutely. Critics argue this is a major philosophical retreat. Tegmark wanted to eliminate all free parameters by postulating that everything exists. By adding the condition must be computable, he has chosen a new arbitrary gatekeeper for existence.
Why should computability, a concept defined by the limits of human-invented machines, be the necessary defining feature of reality?
It seems less baggage-free than he intended.
It does. And the restriction to computability also excludes the vast majority of mathematical structures, including most real numbers, which are non-computable. So if the CUH is true, it implies a fundamental discreteness to reality.
Which is not yet confirmed by physics, but it is highly suggestive of a digital universe.
Okay, let's pivot to another technical hurdle that plagues all multiverse theories, especially level 4, the measure problem.
If there are infinite universes, how can we calculate the probability of observing ours?
The measure problem is an existential crisis for the MUH. If the ensemble is truly infinite and all structures exist equally, then the overwhelming majority of mathematical structures must be complex, chaotic, and messy.
They would vastly outnumber simple ordered ones like our cosmos. So if you randomly select a structure, the probability of finding ourselves in one governed by simple, elegant, stable laws should be basically zero.
This is the infamous Boltzmann brain problem, but amplified across infinite realities. We should expect to be just a chaotic fluctuation that momentarily exists purely due to random chance before dissolving.
Not existing within a stable 14-billion-year-old ordered cosmos?
So to solve this, Tegmark proposes weighting the universes by their Kolmogorov complexity. He has to reintroduce simplicity as the selection principle for reality.
We have to define this carefully. What is Kolmogorov complexity?
In information theory, the Kolmogorov complexity, let's call it K, of a structure S, is the length of the shortest computer program, written in a specified language, that's required to generate or describe that structure.
And Tegmark proposes a weighting formula. The probability of observing a universe is inversely proportional to 2 raised to the power of its complexity.
So P universe is proportional to 2 to the power of negative K universe.
This means simple universes, those generated by short, elegant mathematical programs, are exponentially more probable or have a higher measure of existence than complex ones.
It elegantly explains the observed elegance and simplicity of our physical laws.
It connects simplicity directly to reality. Our universe is simple because complex structures, while mathematically possible, are negligibly rare in the ensemble. However, this is where the critiques really sharpen.
What's the problem?
Kolmogorov complexity is mathematically defined as often being basis-dependent.
Basis-dependent, meaning what?
The length of the shortest program depends on the specific programming language or the specific universal Turing machine you choose to encode it.
But wait, if Tegmark's goal was a description free of human baggage, relying on a measure that changes depending on the human-invented coding language,
it fundamentally undermines the rigor of the whole approach.
if the selection rule for reality depends on the programming language used to define it, doesn't that just make the final measure of reality arbitrary all over again?
It does, which is why critics argue that the measure problem remains unsolved, even with the elegance of the complexity argument. If you can't define a truly universal, baggage-free simplicity measure, the probability of us finding ourselves here remains near zero.
The MUH clearly touches upon the deepest questions of existence and the limits of science. This naturally generates immense polarization.
It's like a litmus test for where physicists draw the boundary between empirical science and pure metaphysics. The reactions are highly charged.
You see a clear split between those who prioritize unification, consistency, and mathematical elegance.
And those who rigorously demand empirical verification and falsifiability.
Let's start with the falsifiability contingent. The critics who see this as a grand example of over-the-top theory.
The famous quote that the MUH is grandiose nonsense comes from mathematical physicist Peter Woit.
And his central critique targets the very nature of level 4.
Right. A theory that predicts everything because all mathematically consistent structures exist effectively predicts nothing specific about our universe. If any observation we make is consistent with the ultimate ensemble, the theory is immunized against empirical failure.
If you can't prove it wrong, it isn't science. That's the classic Karl Popper criterion.
Exactly, and the high-profile science popularizer Sabine Hossenfelder takes an even sharper, more philosophical tone. She dismisses the MUH as fundamentally religion or faith.
That's a very strong accusation. What's the substance behind her view that the MUH violates scientific principles?
Hossenfelder argues that the statement, reality is math, is linguistically empty when it's applied to an unobservable ensemble.
How so?
Well, if experimental physicists probe reality and fail to find a mathematical description for some phenomenon, say, the source of dark energy Tegmark supporters can always just respond, "We just haven't found the right math yet, but it exists somewhere in the ensemble."
It's robust to failure, but at the cost of being scientifically useful.
And moreover, she opposes the postulate of unobservable universes entirely. The Level 4 multiverse, by definition, contains structures that are infinitely inaccessible to us. For Hassenfelder and others, postulating existence where there can be no empirical link moves the theory outside the domain of verifiable physics.
And into metaphysics, making it indistinguishable from the philosophical Platonism that predates the scientific method.
But on the other side, the supporters are often the same figures who are pushing the boundaries of physical possibility. What makes the MUH so appealing to them?
The appeal lies in the ultimate unification and the elimination of those free parameters. Theoretical physicists associated with theories that already suggest multiple universes, like string theory.
People like Michio Kaku and André Linde.
They often view level 4 as the most logical, self-consistent extrapolation of the level I and level 2 ideas they already accept.
If we accept the possibility of varying constants, like in level 2, the next logical step is varying the laws themselves, which is level 4.
The acknowledgement from figures like Edward Witten is also really significant.
Very much so. Witten called Tegmark's work inspirational, likely appreciating the radical intellectual consistency and the mathematical elegance required to define reality based on abstract forms. It appeals to that Platonic instinct that's inherent in many theoretical physicists.
The belief that the most beautiful equations must be the true ones.
And we also need to recognize the strong connection that the CUH, the computable subset, has to information theory.
The idea that the universe is fundamentally an information processing system.
It aligns perfectly with the it from bit philosophy, famously advanced by physicist John Archibald Wheeler. Framing reality as a computable structure is a powerful synthesis for information theorists. The information is the math, and the math is the reality.
Okay, let's move to the most nuanced philosophical critique, which is the category error argument. This is raised by proponents of ontic structural realism, or OSR.
And this is a critique coming from people who largely agree with Tegmark that structure is primary.
This is a crucial distinction that you really need to understand. OSR philosophers, like James Ladyman and Don Ross, they agree with Tegmark's Pillar 2, that structure and relations are primary, and the relata, the particles or substances, are secondary or non-existent.
They are structural realists.
So where does the philosophical divergence happen?
The category error is collapsing the distinction between physical structure and abstract mathematical structure. OSR thinkers maintain that physical structure is instantiated reality. It has causal power, it exists within space-time, and it's subject to the dynamics of physics.
Whereas abstract mathematical structure is merely a potentiality, the realm of possibility.
And Tegmark collapses that distinction by saying they are identical.
To him, causal power is just another mathematical relation within the structure.
Exactly. To him, the distinction between a structure that is instantiated and one that is abstract is just more human baggage. His position, often called mathematical monism, relies heavily on the work of philosophers like Stuart Shapiro,
who argue that a mathematical structure is simply a collection of places, defined entirely by their relations, fitting that baggage-free description perfectly.
But for the OSR critics, ignoring the distinction between abstract possibility and concrete, causally active reality is the fundamental error.
Given all this intense philosophical debate about falsifiability, what actual observable predictions does the MUH make about our universe that we can actually test?
Tegmark argues that, despite the infinite scope of Level 4, two key testable claims emerge because of the Kolmogorov complexity weighting.
The first is the prediction of regularity.
The MUH posits that reality is fundamentally mathematical. Therefore, as we probe deeper into physics at higher energies or smaller scales, reality must continue to be revealed as purely mathematical.
We should never hit a wall of chaos or magic or some phenomenon that fundamentally defies quantification or symmetry groups.
We should only find more symmetries and more elegant equations.
And so far, the history of 20th and 21st century physics seems to confirm this. Every time we build a more powerful instrument, we find a deeper layer of mathematical elegance, like the Standard Model or the conformation of gravitational waves.
It holds true so far. However, as critics like Hassenfelder would point out, this prediction is robust to failure in a way that limits its scientific utility.
If we find something that defies current mathematical description.
The MUH simply dictates that we must invent the new mathematics that describes it, which renders the original prediction circular.
The second prediction, relying on that Kolmogorov complexity weighting, is the prediction of simplicity.
Since simple universes, those with low complexity generated by short programs, are exponentially more probable, the MUH predicts that the ultimate theory of everything for our specific universe must be short, elegant, and of extremely low Kolmogorov complexity.
It can't be a messy, complex set of rules.
What's the status of that prediction? The current standard model, though effective, doesn't feel particularly simple.
It's highly elegant in its structure, but it still contains about 19 arbitrary parameters, the masses of the quarks and leptons, coupling constants, and so on.
And the precise values are not predicted by the theory itself. This suggests that the final, simple answer is still missing. Furthermore, attempts to find a unified theory, like string theory, often reveal a landscape of 10 to the 500 possible vacuum states.
Which is the opposite of a short, simple solution.
The search for that truly short, elegant fundamental equation is still the key test.
Finally, let's discuss the connection between the MUH and Tegmark's other work in artificial intelligence, particularly his focus on AI safety and the Future of Life Institute.
His work on AI is a direct philosophical application of the MUH. The core concept connecting them is the substrate independence of consciousness.
Right. We define consciousness as a self-aware substructure, a mathematical pattern.
Precisely. If consciousness is fundamentally a mathematical pattern defined by relations, it is independent of the underlying physical substance. It doesn't matter if that pattern is executed by carbon-based biology or by silicon-based machines.
So understanding the math of consciousness is crucial for safety.
Yes. If we can understand the mathematical structure of sentience, what constitutes a self-aware, goal-oriented pattern, we are better equipped to control and align the powerful AIs we create. It becomes a problem of mathematical engineering, not just biology or psychology.
And this also explains his interest in the AI physicist, using algorithms to discover physical laws from data.
That empirical work reinforces the underlying MUH idea. If the universe is math, then mathematical regularity should be easily and efficiently extractable from physical data, even by a non-human entity. The ability of an AI to discover the fundamental laws of nature suggests those laws are inherent in the structure, not imposed by the human mind.
Max Tegmark's mathematical universe hypothesis is a powerful, unified piece of mathematical monism. It solves Wigner's profound puzzle of effectiveness. It eliminates the ultimate question of where the laws come from.
And it reduces all of reality to the necessary, eternal realm of mathematical possibility.
The trade-off for this elegant unification, however, is substantial. It requires accepting an infinite, unobservable, level-fay multiverse, and it places immense tension on the core scientific demand for empirical falsifiability.
The debate really centers on whether this is the final, ultimate logical step in the Copernican revolution reducing humanity's subjective role to zero, or whether it is a grand philosophical overreach that transcends the boundaries of science.
Ultimately, the MUH asks you, the listener, to accept that your personal subjective experience, the sensation of time flowing, the deep emotional pang of happiness or loss, the fire of existence, is simply the user interface for a deeper, colder, and eternal mathematical structure.
As we continue to test the boundaries of physics, searching for that elegant, simple theory of everything, we have to ask ourselves, if the universe is a program, where do you draw the line? Where does the mathematical code stop and the stuff begin?
Thank you for joining us on this deep dive into the ultimate structure of reality.
We hope this has given you a clearer, more rigorous understanding of Max Tegmark's provocative idea, something you can mull over and explore on your own long after the equations stop.